Unfortunately, for far too many others, life has become hopeless. And as long as the foreseeable future. This report was produced by Mary Ferreira for the United Nations.
Have to carry on with the work. In the previous period, we had a look at the apparatus very quickly. What did we say do we use to measure time with? A stopwatch, all right? And it can be a digital one, or it can be an analog one, a digital one, and an analog one. It doesn't matter, but remember we said that when we measure, our limit of accuracy is 1/10 of a second, even though it can give 100th of a second. No, all right. That's just due to you. We said we use a thermometer. What is the SI unit for temperature? Kelvin. Okay, and I explained to you at 0 Kelvin, particles have no energy, all right. And from there, there's a direct proportionality in the terms of the temperature in Kelvin and the amount of kinetic energy the particles contain. The next quantity was mass. Mass is the amount of matter, and it's measured in kilogram. The apparatus we use is a balance, all right. Then we said volume can be measured using a measuring cylinder or a burette and a pipette. I don't want to say much more about that. Just remember when we work with a burette and a pipette, if you run the liquid out, you don't blow out the last drop. There's always a little drop stuck in the bottom of the apparatus, but it's been calibrated with that drop left in it. No. Unit for volume, cubic, centimeters, meters, or millimeters. And then we had a look at purity of substance. If something is pure, it means it consists of one kind of substance. It has a fixed boiling point. If you want to separate the substances, if it's a compound, you need to break chemical bonds. All right, they occur in a fixed ratio in a compound. If we have an impure substance, it's usually mixtures. When we have a mixture, it's two or more substances put together, no chemical bonds. We find that mixtures melt and boil over a range of temperatures. Okay, so that is where we stopped in the last period. Now today, I want to carry on. We are still busy with pure and impure substances. One of the properties then, if something is pure, is that it melt and boil at a fixed temperature. That's melting point, and the upper one is always the boiling point. All right. Why is purity important? If I want to bake a cake, the recipe says 2 cups of flour and 1 cup of sugar, but if I messed some salt in my sugar, I took a cup of the sugar-salt mixture, will my cake taste the right way? Now, it won't be very poisonous, but let's say I am making medicine, and the medicine has got a specific recipe with specific chemicals in it, then I will find that if I don't work with pure substances to make my medicine, I can end up making something that is quite poisonous. All right, so when we are working with something that is pure. And to check to see whether something is pure, we have to go and have a look at fixed melting points and boiling points. If I look at this graph, what substance do you think we check the melting and boiling point of on this graph? Yes, why do you say that? Yes, remember, water melts at 0 degrees Celsius and it boils at 100 degrees Celsius. Okay? At sea level, I'll explain something to you in a moment. Yes, if it is pure. Okay, now, before we go on, I want to, in terms of when a liquid boils, when I said water boils at 100 degrees Celsius, there was a query, does it always boil at 100 degrees Celsius? Does water always boil at 100 degrees Celsius? No, it doesn't. In fact, people climbing Mount Everest have quite a big problem with water boiling because there it boils at like about 60 degrees, so it's not hot enough to cook their food. Okay? How does it work? At what point does a liquid boil? What factor influences the boiling point? Air pressure, or the pressure on the surface of the liquid. If it's an open container down here on Earth, it's air pressure. We know if you go to Swakopmund at the coast, the air pressure is more than inland. The pressure is very slightly less. You also know if you go to the sea and you make yourself a cup of coffee, you burn your mouth. Why? Even if you make it with the exact same proportions, the water boils at a slightly higher temperature. So when does a liquid boil? It's fairly simple. If I have a container, okay, and I heat it up, I've got some, let's say, water in this container. When I start heating it, if you could look in the container, go home this afternoon and put some water in a pot, okay? And initially, you find tiny little bubbles appear on the surface, on the bottom. What is in that bubble? Where does the air come from? Water vapor. Yes. In that little bubble, what happens is the heat from the heating source heats up the water at the bottom first. So some of those particles gain enough energy can overcome the attractive forces and they make a little bubble of water vapor inside the water, or whichever liquid it is, it would be the vapor of that liquid. So, say again? Yes, because some of it will escape eventually. Now, this little bubble starts rising up and then it disappears. Why does it disappear? As it goes up, the water is cold, so the vapor inside that little bubble condenses and it forms a liquid again. But eventually, as this water now starts heating up, okay, and we get more or less the same temperature throughout, at a certain point, the water inside this container has enough energy to cause a little bubble of which the vapor pressure inside the bubble is equal to air pressure or the pressure on the surface of the liquid. And at that point, a liquid will boil. So, if I have a pressure cooker or in a car's radiator, the pressure on the surface can become much bigger before the liquid will boil because it has to be hotter and hotter and hotter and hotter before there is enough pressure inside the bubble for it to burst open on the surface. Do you understand? So that is why pressure influences boiling point. In general, the higher up we go, the less the pressure. So what's going to happen to boiling point? It's going to become lower because the little particles of vapor in that bubble needs less energy to get the same pressure to be able to burst open on the surface. So technically speaking, a liquid will boil, not specifically at a temperature, but a liquid will boil when the vapor pressure inside the liquid is equal to the pressure on the surface of the liquid. Does it make sense? Okay. So just very simply in terms of class and we're busy with science, when I talk about the boiling point of water, I actually mean the boiling sea level. Okay? Yes. Near, it's going to boil much faster. No, it's going to take much longer. Yes. They'll be able to get hotter and hotter. Yes, yes, yes. That's what they do when they distill water in a factory. They don't boil it up to 100 degrees Celsius because it's too expensive. So to distill water, they do it at negative pressure. Understand? Yes, yes, yes. Okay. All right. So that is with a boiling point of a liquid. Okay, now we say if something is, it has a fixed melting and a fixed boiling point. All right. When I have, let's take for example water, and I go and add some sugar into that water, and I go and test to see what the boiling point would give me now, I will find that more or less here, above and beyond its boiling point, it's usually going to go slightly above it, not lower. We find in general that impurities, now let's make our impurities, make them blue. Okay, impurities lowers the melting point, but highers the boiling point. So what do impurities do? It pushes the melting point and the boiling point further apart. All right, so that is why the boiling point on this graph, it's impure water, is above 100 degrees. And does it give me a steady amount above 100 degrees? No, you can see it's not fixed at one specific amount. So we say, if a substance is impure, the easiest way to check purity is if it's got a reasonable melting or boiling point, is melting and boiling point. Okay? If something is impure, it melts and boils over a range of temperatures. All right. In the European countries where it becomes very cold in the winter and the water on the roads freeze and it makes ice, what do they throw out onto the road? Salt. What does the salt do? It dissolves in the water and it pushes the freezing point down, so it doesn't freeze at 0 or -1 or 2 degrees Celsius. What do we do in a car's radiator? We add antifreeze. Why do we add antifreeze? Because in the winter, when the temperature drops radically, it goes below 0 degrees, what's the water going to do in the radiator? It's going to freeze. What does the antifreeze do? It prevents it from freezing because it lowers the freezing point, maybe let's say down to -20 degrees. So here by -1, 2, 3, 4, 5, 6, 7 degrees, it does not freeze. Okay, the antifreeze that we add is an impurity to the water. It pushes the melting point down and the boiling point. This is in your textbooks. They're on page 60 and 61. There they have the graphs with the melting and the boiling point. No? Okay. And, all right, now, the next thing that we have to have a look at is, if something is impure and I want to try and purify it, how do I do it? It sort of depends on what you've been given. If, for example, I have a mixture containing water and sand, one way of doing it is to filter off the sand. Okay. But the sand is insoluble, so it will be left behind in the filter funnel, and the water that is soluble will run through. Would I be able to separate a mixture of, let's say, Oros and water with filtration? No. Why not? The Oros is soluble in the water. So when will we use filtration? When the insoluble substance is mixed with a liquid. Do you understand? If I had a bit of petrol, 2 cups of petrol, in the one I add a spoon of sugar, of salt and I shook it up, the sugar is going to dissolve. Can I get the sugar out from the petrol by filtering it? No. Can I get the salt out from the petrol? Yes. Why? Because the salt is insoluble. No. So when do we use? Is if we have a solid substance that does not dissolve a liquid. No. Whatever the solvent is. Now there are specific terms when we want to filter. The apparatus is a funnel, a glass funnel. You could also call it a filter funnel. Sometimes they're made from plastic. It doesn't really matter. Okay? Then we have a filter paper that is put into the filter funnel. You fold it up into the shape of a cone. Okay, and it fits into the funnel. And then you go and pour everything, your whole mixture, through the filter containing the filter paper. We find that the solid part, the sand for example, is going to be left behind in the filter. Okay? The sand is left behind in the filter. We call the sand, the stuff that is left behind is called the residue. You must know the term, no? And then the stuff that runs through is known as the filtrate. In this case, if it was sand and water, sand is the residue, water is the filtrate. Another way of separating substances is by a process known as crystallization and recrystallization. Now, have you ever seen, if you go to Walvis Bay and Swakopmund, especially there in Walvis Bay, there are certain areas in Swakopmund that as you drive along the coast out of Swakopmund, you find there are pools of water, okay? And sometimes they've got different colors. Some of them are like slightly pink and the others just look like the color of water. They are busy with a process known as crystallization. Now, how does crystallization work? If I take, let's say I've got water and normal table salt, okay? I take the water and I add table salt to it. I stir it. The table salt will dissolve. I add some more table salt. I stir it. It's going to dissolve. I warm up the water. I add some more table salt. It's going to dissolve. Okay, now, once all the table salt is dissolved in the water, I say to you, okay, now I want you to extract the salt from the water. What are you going to do? We are going to evaporate the water. Will the salt evaporate? No, it's a solid. Solid substances don't just evaporate. Okay? So what we are going to do when we talk about crystallization, we are going to remove a soluble solid that is dissolved in a liquid. We are going to remove it from the liquid. For example, salt from water. And now, the basic steps. We heat the solution. This beaker containing salt and water, we heat it up. Why do we want to heat it up? Yes, we want the water over here. The water is evaporating. What is left behind in the basin? Over there, the salt will be left behind. But also, as we heat up the solution, the stuff becomes more soluble. Okay? But at a certain point, when you've evaporated usually about a third of the solution, you will have what we call a saturated. It means no more can dissolve. Okay? A saturated solution. Now you remove the heat source over here. You allow the hot solution to cool down. As the liquid cools down, the solubility of the salt in the liquid becomes less. So it starts forming crystals. Okay, so it will crystallize, you will pour off the rest of the liquid, and you will be left with pure crystals. Okay, that is crystallization. Now, recrystallization. If I take my crystals that I get from the first step, I dissolve them in water because sometimes there are impurities sticking onto their surfaces. All right? I take them, I redissolve them in a bit of water. I start heating up the water so that I can get a saturated solution. Then I take it and I leave it to, and it will crystallize. And if there are any impurities, they are usually dissolved in the liquid. I pour that off and you have your crystals. Something about the recrystallization in a moment. Recrystallization in it. Let's say I've got some sodium chloride in it, I've got some potassium chloride in it, I've got some magnesium sulfate in it. All of them dissolve. Okay? But some salts are more soluble than others. Okay? So if all of them are added to the solution, they all dissolve. I heat the solution to make them all dissolve. Okay? Then I allow some of the liquid, allow it to cool down, and I will find a specific salt will form crystals at a specific temperature. Because we will find the one that is the least soluble, the one that doesn't really want to dissolve very well, will crystallize out first, and you can filter it off. Then the next one, the next least soluble one will crystallize out. And lastly, the one that is the most soluble. Now, if you've looked at the pans of water there in Walfish Bay, sometimes you will see some of them are pink. Because what they do is they allow the sun to evaporate the water, so they don't use energy. And the first salt that crystallizes out, I don't know which one it is a specific salt. The water becomes pink because of the dissolved salts in it. Then they run that water off into a next pond, so they can remove that salt. And then they allow it to evaporate off more. And the next salt crystallizes. Verstaan julle? Okay, and so on. They can remove the different fractions. But now, that first lot that you remove won't be very pure. There's going to be contaminants from the liquid and the other salts dissolved in it. So they will be redissolved and recrystallized to get them to be fairly pure. No. Okay, so crystallization and recrystallization. Recrystallization, an impure compound is dissolved in a hot solution, or two or more substances are dissolved in a hot solution. Then they are cooled, allowing the substances to crystallize. Which one will crystallize first? The least soluble. It doesn't want to remain dissolved. The next one, the next one. No. Okay, so a hot solution is used because the solubility increases with an increase in temperature. As it cools down, it will crystallize, and remember, the least soluble one will always crystallize first. Okay.
Prevention is important. Help prevent the spread of illness and keep yourself and others well. Hand washing is one of the most effective ways of preventing the spread of germs. Wash your hands regularly with soap and hot water, scrubbing your hands thoroughly for at least 20 seconds. Hand sanitizers can be used but are not recommended as a substitute for hand washing. Use sanitizers in addition to hand washing or in a situation where soap and water are not available. To avoid spreading germs, limit sharing of personal items such as utensils, cups, and dishes. Your skin acts as a barrier to germs, but your eyes, nose, and mouth are more vulnerable. Wash your hands thoroughly before touching your face, eating, or drinking. Avoid physical contact with others, including handshakes, fist bumps, high fives, hugs, and kisses. Social distancing is deliberately increasing the physical space between people to avoid spreading germs. While regulations may vary by country or area, the best guideline for social distancing is to maintain a distance of 6 feet from others. Germs can travel to another. If you sneeze or cough, do so into a tissue or the inside of your elbow to prevent the spread of germs. Avoid contact with ill individuals and insist they isolate themselves until they have recovered and are symptom-free. And workplace several times a day. Share these guidelines to prevent the spread of illness and maintain a healthy environment. An ounce of prevention is worth a ton of cure.
The mighty Zambezi River, the longest east-flowing river in Africa, a river that flows through 6 countries, home to a plethora of wild species of fauna and flora, a lifeline for many people whose livelihoods are dependent on the abundance the river brings. Globally, communities who live along rivers rely on these rivers to survive. Communities living along the Zambezi call it the river of life, bringing water for their crops and fish as their main protein source. In Namibia, a country situated in sub-Saharan Africa, the Zambezi River sits at the heart of Kaza, the Kavango-Zambezi Trans-Frontier Conservation Area, which is one of the greatest conservation areas on Earth, a stronghold for very many of our most iconic wildlife.
I'm right now where the river forms the border between Namibia and Zambia. This enormous water body provides sustenance to a wide array of wildlife, bird and fish species. It's also a lifeline for human beings.
The same communities are the people also who are doing the illegal activities.
The price of fishing has gone up because fish has become scarce.
The more they finish, that's the more our life gets harder and harder.
These days, it is very rare to get a big bream unless in those protected areas.
A small group of community members, together with non-governmental organizations like Namibian Nature Foundation, are fighting back.
We have to start thinking out of the box, to be honest, because what's going to happen is going to be out of this box that we haven't seen before.
By creating protected areas, monitoring and patrolling, fish stocks have a chance at recovery. These are the stories of the people fighting for the continued existence of their communities. These are the last defenders.
Struggling with no food, no what. But we didn't stop. If I don't do it, our young children, they'll never know the fish.
In your favorite rapper, many dollars that you are capping up his head.
Tu come